Okay, now let's study the one of the most important class of analytic functions, the Mobius transformations. So 3.5 definitions. Okay, a mapping of the form a mapping of the form S of Z equal to AZ plus B over CZ plus D is called a linear fractional transformation. Linear fractional transformation. Okay, so linear, numerator and denominator are linear functions. Fractional, you have a ratio. Okay, so linear fractional transformation. And if A, B, C, D also satisfy AD minus BC is not equal to 0, then S of Z is called a Mobius transformation. Okay, if AD minus BC is not equal to 0, then S of Z is also called a Mobius transformation. What is the meaning? Why we require such thing, then we give it a different name. Okay, well, to understand this, let's try to do the long division. Oh, it's not very long, it's short. We divide AZ plus B by CZ plus D. What we get, we're going to have A over C, okay, then A over C, then let's see. A over C times CZ is AZ. A over C times D plus AD over C plus AD over C, and B minus AD over C. All right, so what it is, so it means AZ plus B over CZ plus D is equal to AC plus this denominator B minus not the remainder, not denominator, B minus AD over C over CZ plus D. Let's write one more step. So it's a BCO minus AD over C squared Z plus CD. So now you can see that if this BC minus AD, AD minus BC, BC minus AD, same thing, almost the same. If BC minus AD is 0, then you have a constant function. If AD minus BC is equal to 0, then this S of Z is equal to AC, a constant function. Okay, well, constant function, of course, it's a linear fractional transformation, but constant function is not interesting. So we do not want constant function. So in other words, a Mobius transformation is a non-constant linear fractional transformation. A Mobius transformation is a non-constant linear fractional transformation. All right, so this condition just tell us this mapping is not a constant map. It's not a constant. Okay. Second, that's an explanation why we have such a requirement. And second, let S of Z be AZ plus B CZ plus D. We define T of Z as what? As DZ minus B over negative CZ plus A. We define this. Well, let's see what we have. We do the composite transformation. S composed with T, so T it's A dz minus B negative CZ plus A and plus B over C dz minus B negative CZ plus A and plus D. We multiply top and bottom by this negative CZ plus A. We'll get ADZ minus AB plus B negative CZ plus A, CDZ minus BC and plus D negative CZ plus D, the plus A plus A plus A. So continue. So ADZ minus AB plus minus BCZ plus AB. It's numerate. Denominator CDZ minus BC minus CDZ minus CDZ plus AD plus AD. Okay, so this term that cancelled. CDZ cancelled, so the numerator becomes ADZ minus BCZ, AD minus BCZ. Remember, we assume this is not 0. This is AD minus BC. They are not 0, they cancel, so you get Z. Okay, very good. So we get the constant, not constant, the identity function Z. Well, of course, I'm not going to repeat it, but you can try it. Ts of Z with this computation, it is also Z. All right, so ST composite function is the identity function. TS, the composite function, is the identity function. So T is the inverse Mobius transformation. T is the inverse Mobius transformation. All right? The inverse of S. The inverse of S. How do we get the inverse of S? Exchange A and D, change the sign of B and C to be negative. Okay? Okay, good. This is the inverse. And the inverse is with respect to the mapping composition. And the other thing, the Mobius transformation AZ plus B, CZ plus D. you can multiply top and bottom by whatever non-zero number. For arbitrary complex number, lambda is not zero, so you will get the same thing, same Mobius transformation or the linear fractional transformation. And this implies, this observation implies this A, B, C, D, the coefficients, we can call the coefficients of coefficients are not unique. The coefficients of Mobius transformation is not unique. All right. Another thing, for the same thing, the AZ plus B over CZ plus D. If Z is equal to negative D over C, if Z is equal to negative D over C, we will have zero denominator. Zero denominator, we will understand it as infinity. Numerator is not zero, so this is infinity. So it maps this point to infinity. And if Z approaches infinity, we have the limit Z approaches infinity, S of Z as A over C, the ratio of the leading coefficients. All right, so these two observations implies that we could consider as this linear Mobius transformation is from C infinity to C infinity. Okay, so it becomes a C infinity to C infinity map with inverse. Inverse is given, where inverse is T is dz minus b over cz minus a. Inverse is already given. All right. If we do not consider it as a C infinity to C infinity, then S is not defined over C. S is defined without negative d over C. So S, the domain is not a whole complex plane. You have to exclude this point. But now you can say it's defined over C infinity. Okay. Then we have several names. Let's see, we have several names. Name one. If S of Z is S of Z is equal to Z plus A, it's called a translation. So C is equal to 0, D is equal to 1. Second, and if S of Z is equal to AZ with A non-zero, of course, then S is called a dilation. Is called a dilation. 3. If S of Z spatially equal to e to I theta times Z, S is called a rotation. It's a rotation. And 4, if S of Z is 1 over Z, S is called the inversion, There's only one inversion. It's called the inversion. Okay, so translation, there's several translation. Dilation, there's many dilation. Rotation, of course, there's infinitely many rotations. But inversion, there's only one inversion. So the inversion. Okay. Okay. Why we are interested in those names is because of the following proposition. Following proposition. So if S is a Mobius transformation, then S is a composition of translations dilations under the inversion. Translation dilation under the inversion. Of course, you may just have one or you have several, right? You may have one or several. Okay, now let's see the proof. This proposition just say if you understand those translations, dilations, or inversions, and if you understand the composition, then you understand everything, right? Okay, so remember that we actually did something. We did this long division. This long division actually I didn't emphasize. We can do this long division only when C is not equal to 0. If C is equal to 0, there's no such long division, right? So that's just an idea. So here we do the similar thing, almost a similar thing. So we are going to discuss C. So case 1, C is equal to 0. If C is equal to 0, then what is S of Z? S of Z becomes A over D times Z plus B over D. So it's exactly the dilation composed with a translation. Dilation composed with translation. So we are done. This is dilation. And this is translation. All right. So now let's see what happens if C is not equal to 0. And second case, C is not equal to 0. If C is not equal to 0, we actually have, where is it? We have that S of Z is equal to A over C plus B minus, what is AD over C over CZ plus D. Remember, after long division, we have such thing. Well, let's read. Dilation, translation, dilation, translation. This is a inversion. Inversion. Here again, this is a dilation and translation. Right? So 1, 2, 3, 4, 5. There are 5 steps. There are 5 steps. We'll get it. Okay, so this is the proof of a theorem, proposition 3.6. All the Mobius transformations can be decomposed as those three types: either translation or dilation or the inversion. We don't say that rotation, because rotation is a special type of the dilation. Okay. Okay. So next we're trying to identify Mobius transformation. Basically, we're going to see which two Mobius transformations are the same. In order to say that, we first start with fixed points. Fixed points of S. Fixed point S of Z is equal to Z. So AZ plus B over CZ plus D equal to Z. Then we will have AZ plus B CZ squared plus DZ, and we get CZ squared plus D minus A times Z and minus B is equal to 0. A quadratic equation. Okay, the quadratic equation means a fixed point must satisfy this quadratic equation. So there are at most two fixed points, right? There are at most two solutions, so there are at most two fixed points. Well, for a general general Mobius transformation. But there's one special case. A special case is that this is an identity. You see, if this is a quadratic equation, two fixed point. If it's a linear equation, one fixed point. If it's an identity, infinitely many fixed point. Right? I say for the general Mobius. What is a special case and what is identity? Identity means it's not quadratic. It's not linear. And the constant must be 0. Right? So if the left-hand side, all the coefficients are 0, then of course this is identity. It doesn't matter what Z you have. So we have C is equal to 0, B is equal to 0, C is equal to 0, B is equal to 0, A is equal to D. And what it is? This corresponds to the S of Z equal to Z. Of course, it has infinitely many fixed point, because this is an identity map. Okay, so how can those fixed point information help us to identify a Mobius transformation? A Mobius transformation, if it's not identity, it will have at most two fixed point. So if we can identify S of Z at 3 points, we uniquely determine it. Right? It has 2. If we can have 3, then we will uniquely fix it. That's the idea about fixed point. The application of fixed point. Okay, so if we want to either name a Mobius transformation, or if we want to tell the difference between Mobius transformation, we only need 3 points. Actually, it also makes sense why we just need three points. Here we have 4 numbers, A, B, C, D. We have 4 numbers, but we only need 3 points. The reason is that, remember that we have the condition AD minus BC is not equal to 0. This condition is very important. This tells us A and C cannot be 0 together at the same time. Cannot be 0 together. If A is 0, C cannot be 0. If C is 0, A cannot be 0. So at least one of them is not 0. Let's assume A is not equal to 0. If A is not equal to 0, remember we can do multiplication or division by whatever complex, non-zero complex number. A is not 0. We can divide this Mobius transformation by A for top and bottom. We get just 3 numbers. If C is not 0, we're going to divide the top and bottom by C. But in any way, you see here, this Mobius transformation is actually determined by 3 complex numbers. By those 3 complex numbers, if you know the information at 3 points, then you will uniquely determine those 3 complex numbers. And that's why we only need 3. That's another explanation why we only need 3 parts. All right. Okay, let's see. Let's see how we get it. So let S be a Mobius transformation. And let A, B, C be distinct points in C infinity. It could be infinite. With alpha is S of A, beta is S of B, gamma is S of C. So you have 3 values. And if T is another Mobius transformation, with the same property, alpha is TA, beta is TB, gamma is TC, then this or whatever the T compose S T compose S, S compose T. T inverse compose S. You see, S of A is alpha. Alpha is TA. T inverse of alpha is A. Yeah, this is A. And the T inverse compose S of B is B. T inverse compose S of C is C. So this composite, the composition of a Mobius transformation is, we didn't mention that the composition of Mobius transformation is still a Mobius transformation, right? And then they have this Mobius transformation has a three fixed point. If it has 3 fixed points, it can only be the identity. T inverse compose S is equal to identity, so T is S. So T is S. So a Mobius transformation can be uniquely determined by the action over 3 given points. And those third point, we didn't mention, we didn't use numbers because we allow the C infinity. Infinity is not a number, so that's why here we use point instead of numbers. Okay. So that is a determination, unique determination, or the identification. Okay, we finished this video at this point, and we finished today's lecture, and we will continue the discussion in the next video. Okay, thank you.